project was done by 4 students, so you have 15 to 20 minutes to present, and after that we have time for question and discussion.
Sir, can you see the slide?
Okay, let's start.
May I have the thesis?
Hello, ladies and gentlemen. First of all, we would like to thank you for your attendance to our presentation today. And our object is, and our topic is application of YOLO version 5 deep learning model to ceramic tile defect detection. We would like to thank our supervisor, PhD Nguyễn and Mr. Bùi Đức Minh, respectively. Our member is Trương Duy Thuận, Nguyễn Cảnh Long, Nguyễn Nhật Quang, and me, Nguyễn Quang. Today, the content we will talk about is introduction, project in detail, result, and conclusion. First, introduction. We are working in IoT my company. They have a requirement from an enterprise producing a ceramic tile, and the factory want a solution to control the quality of the factory output product. And we have such many available solutions in the world. And here is two of them. The first one, detection of surface defect based on a pre-trained model. And the second one, they propose a new model to detecting. As we can see, with the rapid development of AI, the manufacturing industry has leveraging their potential to enhance its performance, accuracy, and flexibility. So, in this solution, in this project, we propose a solution to apply a deep learning model to detect the defect on ceramic tile. Thereby, this helps to reducing labor costs, automating quality control process, and finally providing data for development process. We have built a data set and we train YOLO version 5 and achieve flexible result with high precision and confidence higher than 80%. Coming to a project in detail, we will present input and output of project, theoretical basic, and implement. First, input and output project. From the execution line of the factory above, our module is focused on the module detection. This module will capture image and then conduct prediction result. And here we can see clearly the output of the project. Ability to detect the presence of various types of surface defect. Store information such as defect type, defect number, or size of error.
The next slide. Next slide. we talk about aspect of model Euro version 5. It contains three networks. The blackboard network to extract the feature of the input image, the net network to refine the feature and combine them across the different scale, and the N network to generate the final output. In the model we show in the project is model Euro V25 M6 because it's faster and requires less hardware resource than the long, and the extra long model it also higher accuracy than the small and the nano model. And in this project we work with the high resolution input image. In the implementation process, it consists of 5 steps: data collection, data labeling, reprocessing, model training and validating, and final we export the model.
At data collection process, we create a notebook for the collecting image process to reduce the effects of the outside factor like dust or naturalized. The equipment used for the image acquisitions is Canon C10D and 18 to 55 millimeter length. After the image being taken, we also apply a 3x3 kernel for the feature enhancement.
Next, to label the data, we use RoboFlow tool, and here is some other function of Robo. The first one is they can generate new version for training. The second one pre-processing. They can augmentation for get a bigger data set, and finally check health test to get a status data set. Classes, we based on effect check characteristics, we divide our data sets into 3 log classes: whole class, HB, and light class. And the right image is the conduct. The conduct classified effect we did.
We conducted several statistics for ensure the balance and accuracy of our data. Consider 19 and 41 which are divided into three smallest data sets: training set for whole, training set for training model, validation set for model validation during training process, and test set for testing and evaluating the model. Monitor will take a look at this table that describes the numbers of instances for the class. In total, we have over 16,000 instances. You can see the lines have less instances than the other one, but it's still in acceptable range. We also consider the annotation in maps to assess the instant distribution. From this heat map, it observes that all instances are distributed across the entire surface. It's a nice work. We apply pre-processing techniques to orient the annotation of variables in the image. Resize the image suitable for the model input, and time image to smaller for improve the detection of small objects. There are some augmentation techniques that we also apply to scale up our data set, scale more number of instances. Thus can improve the learning ability of our model. Then we generate the augmentation data set and ready for training stage.
In training stage step, we will set up environment in the train and training on the Google Cloud, and they resources provided by Google Cloud. And below, there are parameters we use during training. Next, to evaluate the model quality, we use the confusion metric. Depending on the relationship between the realistic label and the real label, it divided into four groups: the true positive, false positive, false negative, and true negative. And they used to calculate the resistance and recall. And then another parameter is the intersection of the union. It used to set the boundary. It measured by divide the overlap of the bounding box and the trust bounding box with the total of the area. And there are table of validation and result. We can see the achieving the line and how the line have achieved a good result with high resistance, while the line had an acceptable result. And the final is a model stack. In here we export the model and use it to predict on image. There are parameters we use prediction, and there are predicted image. We can see the model can detect most defect. But in process of prediction on that image, we found two the problem. The problem is difficult to detect small, to very small size defect. The main reason is small object have a fewer pixels, so the model capture fewer pixels. The second problem is confuse defect with the pattern on the surface. The reason is the pattern has a structure similar with the surface defect, just like a right line. So to improve the model, we will apply proving method into the variable processing step. There are sliding window, also method, and SFA matrix method. Continue to the also method and HFA method. When we apply it into the model, they don't have a good result and it's no problem to the model. So in the final result, we don't apply them. Next to the sliding window method.
Sliding window is a common and powerful technique in math and several algorithms. Fundamentally, it works based on the mechanism of split a big problem into smaller problems by iterate a window over the object, then perform the function in each window. The image is a matrix of pixels, so we can look over that matrix. So let's take a look at the implementation of this technique. We define the window size and the sliding strip. Then we raise the image by OpenCV and initialize the window at the top left corner of that image. Then we move the window over the image with a strip, and in each of these moving steps, we run the predictor to predict the content in each small part of the image in this window. So finally, we combine all the prediction value for final results. That's about with our thesis. So we go to the next session to see the results.
After the first step, we achieve the baseline model with the results so above. We can see in average, this model actually would result in achieving and whole glass. This had high MIPs at 50% overlap, and the precision occurs, so the boost balance in the trade-off. With the line class, it had low average result, and MAPs of this class are not too high. And with the recall and precision curve, we can see the trade-off between the recall and precision of this class be imbalanced. With the confusion matrix, we can see the edge shifting and the whole class boundary classification was learned well by the models, and the line class are being confused with the backgrounds. Here is the sample of the prediction of the baseline model. We can see that it can detect most of the objects on the high surface, but it's still missing some small hole objects, and it can only detect the top of the line objects. Now is the result of the model with line winner techniques. In average, this model also achieves good result in edge shifting and whole class. It has higher MIPs compared to the baseline models, and the balance in the trade-off between precision and recall of this class are improves compared with the baseline model. Although the line class has the lowest result, and the trade-off in the precision and recall are still imbalanced, but compared with the baseline models, there are still a slight improvement. With confusion matrix, we can see that the edge shifting and the whole class classification boundary are still learned well by the models, and the confusion between the line and the background are being reduced. Here is the sample of the sliding windows model prediction. We can see that the normal side class line holes has higher confidence, and it also can detect smaller side objects, and the line class can detect more. To compare the performance of the baseline model and the model combined with the sliding windows, we run them through a test set containing about 96 images of ceramic tiles. Overall, both models have good performance. First, when we can see that the overall precision of the sliding windows are 20% higher than compared with the baseline models. And the edge shifting and the whole class have the remarkable improvements. They all have precision higher than 0.9. After inspect the output test file of the both model, we found out that the small objects detected by the sliding windows model are 60% higher than the baseline model. And this model also able to detect the smallest objects from the 50 to 50 pixels, compared with the baseline model only able to detect smallest object from 75 to 75 pixels. Finally, this is the example of the different in performance of both models. We can see that after applying the sliding windows, the detection ability of model is enhanced. Finally, we will use the Euro V5 M6 model combined with the sliding window techniques for our projects. Is the complete process of our project.
To evaluate the performance on production environment, we deploy the model on a device that these have hardware specification. and the required practice and libraries are also installed. We also export the model to Python formats for speeding up CPU running and tensor time format for speeding up GPU running. The time consumption is from 15 milliseconds to 19 milliseconds for high resolution image. The model can the model run in the device and we can interact with it by command interface or user interface. And final the results contain the class name, object coordinates, and different computer values are saved in the size file for further using this analysis. Now for visual observation, we wanted to demonstrate the user interface, and I need some second to share my video.
Mình là một em chịu cái này trên máy chiếu xong rồi ngoài máy này cứ để nguyên máy này là cái nồi em xem là một em bé máy của em đặt được các cái này.
Chắc là nó không rõ được đâu anh, nhưng mà cái có login vào cho cái team được đúng không? Thì share trực tiếp trên đó, share hình thôi, còn nó không có phải.
Phải mời ông bố rồi cái vào em rất xin phải mời ông bố.
Ông đang ở trong cái Steam cùng luôn mà.
Đang sáng mà. Nhưng mà MS Team này và MS Team này khác nhau mà.
Có vô luôn, share trực tiếp.
So let's take a quick overview. And this user interface. First, we have a main error for display the original image and predicted image. At the bottom left corner, we this arrow for configuration, and at the bottom right corner, we display the result in text file. First, I choose the image for predictor. Next, we can choose which model we want to use, and we have to adjust the confidence and IQ threshold for better inference results. We can see next image. We click this button and we run the predictor. As per time, it's like a lot of time to visualize everything. So here is the results. As you can see, there are some small objects like this hole or some small line in here. This model can predict them, and let's see another image. Here is also here is some small. I will straight into the sliding window and predict again to see the image. Next one. You can see there are more line and small hole are predicted, and the model integrated with sliding window is better than the baseline model. And here inference results contain the class number, the object coordinate, and confidence values. We can use this for further business analysis or indicate the manufacturing process. And now I will back to my slide. And next, to summarize, our work on this project have reached some achievements. We meet the output requirements of the project. Complete training the model for detect and classify the defects. We achieve high resistance with performance improved tactics lab. Besides that, there are several limitations. As you can see here, and from this limitation, we define project work to enhance performance of our projects. First, about ourselves, we need to learn more in depth insight about artificial intelligence and deep learning model. Secondly,